Great. Yes. Okay. So, so thanks everyone for coming. Today we have Zhicheng Zhang from University of Technology Sydney presenting the first class in this mini course. So go ahead, please.
Okay. Thank you, Liron, for this introduction. I'm Zhicheng, and today, this is a mini course on quantum recursive programming, and sorry. So the topic is quantum recursive programming. Yeah, and I think there should be like 5 lectures in total. In this mini course, I will cover several aspects of quantum recursive programming, including first the definition. So what is quantum recursive programming? And several examples. This is to show you why we need quantum recursive programming. And also, I will tell you the implementation. So that is how to implement a quantum recursive program. So probably we will spend like 2 lectures on these 2 parts and 3 lectures on the 3rd part. Okay. And just a disclaimer, so what I'm going to talk about in these lectures is not for how to program today's or existing quantum hardware. It is for probably the quantum computers in the future. Yeah, okay. So I will also, not assuming any background from the audience, I will first go through some background in quantum computing and programming languages, and finally we will start to on our topic. Okay, great. So let's start with the motivation. So the first question is why we need quantum computation? Or here we focus on why we need quantum algorithms. So there are a lot of existing quantum algorithms, like I think most of you probably heard of the Shor's algorithms, Shor 94, for factoring a large integer, and it has some like exponential speed up over the best known classical algorithm. I'll just write it the complexity here. And another famous algorithm is called Grover algorithm for searching an unstructured database. Grover, 96. This is a search algorithm, and it has some quadratic speed up over the best known classical algorithms. Okay, and we have a lot of other quantum algorithms. And these quantum algorithms, they can achieve some computational advantages on specific problems. So that's why we need quantum algorithms, so that's some computational advantage. By the way, can you see the board clearly? Yeah. And during the talk, please pause me anytime if you have any question or comments.
I actually have a question.
Sure.
So you mentioned that the programming you are about to explain cannot be applied to current quantum computers. Can you explain?
Yeah, I will explain more. So it is not, I'm not saying it is not applicable to the current computer, but you know, the current existing quantum hardware, they don't only have a very small number of qubits. So in this case, unless you scale up this quantum computer, then it can perform some meaningful computation. Actually, in the current quantum hardware, we can only demonstrate some very small examples of quantum algorithms. So we cannot even factor in a large number, like running a Shor algorithm, because current the development of fault tolerance, and yeah, the fault tolerant quantum computer is still in development. So when you talk about programming, it's mostly about you are trying to using the program to describe some very complicated computation. That's why we will talk about why we need programs. So it's how you conveniently describe some complicated computations. So that essentially implies you are talking about something, some very large computations. Yeah, but this is a theoretical framework. So of course it can be applied if you scale up the quantum computers. Yeah. Advantages on specific problems. Okay, and the second question is why we need programming. Here, this is essentially the same question for why we need quantum programming. So I just put quantum here. Quantum programming languages. So okay. So languages, programming languages as a language, so it is a way of how we think about the computation. So it is a way of thinking. And suppose we are here a human and we want to control the computer, and we want to tell it how to perform some computation. And then programming language is a bridge between the human and the machine. So the programming language provides a way to a more high-level way. Here we are mostly focused on high-level programming languages. So it provides a high level, and we want it to be a convenient and accurate description of the computation. So there are other ways to describe an algorithm. For example, you can write it in the natural language, but that must contain some ambiguity. And if for two different persons who look at this algorithm, they might have different interpretation of it. And we also want it to be convenient, so we don't want it to be, so the design of the language should be, it should be simple and elegant. So since it's a bridge between the human and machine. Okay, and on the other side, once a human has written some programs, then this program should be implementable on a machine. So this is often through the so-called compilation. So this compilation process can implement a program. It can compile a high-level program into some low-level one. So in classical computers, we will compile it into some instructions in the instruction set supported by the machine. Then this machine can run these instructions. And so this is more from mid to low level. Okay, great. Now the third question is, why recursion? So recursion, in our context, specifically refers to the so-called recursive procedure calls. So it is kind of programming features. And of course, the history of the general concept of recursion goes back to much earlier, but the recursive procedure calls is a programming feature introduced since the development of the programming languages. And so here we need to, I will write it here. So actually we are considering the concept of structured programming. So a program has structures, and the structure allows you to have a more easier understanding of what the program is doing. So that's for the convenient part and accurate part. So if the program has no structures, then even for a very smart person, it is hard to understand what the program is doing, and it is hard to design this program. So it's just like the mathematical proofs. You need the structure to handle a very long programs. Yeah, and okay, so recursive procedure calls is a feature of these structures. So here I will give you some examples of classical recursion. For example, we want you might want to compute the greatest common divisor of two natural numbers. So you can use a Euclidean algorithm, which can be written like this. So you want to compute greatest common divisor of A and B, then you can check if B is 0, B is 0, then you return. Then you return A, else you return So this is a classical example of recursive programs. Yeah, and okay. So here, if then else, I hope most of you might be familiar with this kind of statement. It just means you check this condition. If B is equal to 0, then you execute this first part. Otherwise, you execute the second part. Yeah. And of course, we have other primitives other than this recursion. Like we also like something, for example. So here we already see this if then else statement. We also have a while loop. We can say while B, this is a Boolean expression. If B is true, then we do some statement. Say, so let's make it concrete. So x is smaller than some number, and then we increment x. Okay. So there are many standard primitives in the classical programming. Okay, so let's focus on the recursion. We can do something more complicated. So this is just the one procedure. So this, you are defining some function using itself. So you are defining GCD-AB using the GCD-BA mode B. But we can write more complicated recursion. So for example, you have two procedures, like PX, and you have another QY. So they can call each other mutually. For example, you can write P, and in the definition of PX, you call the Q. Like you call QX minus 1 and do some other things. Or in the definition of QY, you can call the P again. Y over 2. Or something like this. You can write arbitrary procedure calls to other procedure or itself. So So that's, and you can see using these recursive procedure calls, it can allow a static program, which is very short, to generate a long and dynamic computation. So this is static program. And you can generate a very long computation, probably even unbounded. So for example, this is a good example. This program text only contains this part. It is short, but if you take A and B to be very large, like millions and billions, then the actual computation carried out by this program, by executing this program, is very long and dynamic. Okay. So I want to also quote a quotation from Dijkstra saying, "I only have a very small head, and I must live with it." So we use these structures to help us using our small head to manage very complicated computations.
So question, are we eliminating the option to use iteration here?
Sorry?
So are we allowed to do iteration?
Yeah. So our focus in this lecture is mostly about the recursion, but other primitives are also available. So it depends on whether you want to include these primitives. But using this recursion and some elementary like assignment of variables or something, it is already Turing complete. But you can also consider include iterations and loops and other kind of primitives.
So would that, would including iteration then make making proofs harder in some setting? And also the other question,
yeah.
Is it easy to take Shor and Grover and phrase it completely as recursion and no iteration?
Oh, good question. So yeah. So actually, the iteration is not the hardest part to deal with even in classical programming languages. And in classical programming languages, the most complicated, theoretically, primitive is while loop, or because it can contain some unbounded loop. And for your question about these algorithms, my answer is recursion can help some part of it, but not all of it. Because even in classical, not every algorithm can be written in a recursive way, but it provides more flexibility, because if you do not write this, for example, for this algorithm, if you do not write it in the recursive fashion, then it might take some longer program to write it down. And it could be harder for you to think about this program, think about this algorithm. Okay, so...
Sorry, just a very quick comment or thought
yeah.
To Yifel's question. So wouldn't it be easy to just use a recursion to encode iterations in an easy way? As you said, this Turing complete, it can be done, we know, but then is it not easy? You just have a counter and then you call it itself and reduce counter by 1 and then
you can write it that way, but that often is not the best way to write the iteration. Yeah, so I mean sure. From the implementation aspect and also from the from the description aspect, iteration, at least because we are all accustomed to the iteration already, so we think it is easier to think about the iteration. Yeah. Yeah, so after all, these primitives are just about how you think about the computation, how you describe it. Yeah, then there are also other famous examples like the horse quicksort. Which is probably the first complicated examples of recursive programs that is implemented in history. And also we have a lot of, I'm still talking about the classical recursive program. There are a lot of recursive data structures. And also, there is a famous paradigm of designing algorithms is called divide and conquer, and this often requires you to use the recursion. For example, we want to divide a large problem that has some parameter, size parameter, and we can probably divide it into two parts, each of size n over 2, and then if the whole, solving the whole question can be using the subroutine to solve each of these problems and then combine them together, then we have naturally have a recursive description of such kind of algorithms. Yeah, okay. So, here are 3 questions, and so we have quantum here, we have programming here, and we have recursion here, and that's why we study quantum recursive programming. And I will show you more examples when we finally get to the details of quantum recursive program. But these motivations are largely motivation for our topics today. Okay, is there any questions so far? Great. Okay, let me start with some background in quantum. So, just the basic part of quantum computation, of quantum computing, and actually I will only include the part that is necessary for our quantum recursive programming. And of course, if you want to have a more detailed understanding of quantum computing, you can check the standard textbook, Zhicheng Zhang. Okay, so I will only mention the quantum states and the unitary operation on quantum computing. So let's start from the very basic ones. So I'm assuming no background from the audience. Okay, so just start from the so let me start from the standard axiomatic approach to describe quantum mechanics. So this is called Dirac von Neumann axioms. So using these axioms, we can describe a restricted version of quantum mechanics. So here we are restricting ourselves to describe the quantum mechanics of finite qubit systems. Restrict to finite quantum system. Okay, so let's start with the first axiom, A1. This tells you what is the state of a quantum system. So the states of a quantum system live in the Hilbert space. So since we are considering finite quantum system, this Hilbert space is finite. And recall a Hilbert space is equipped with an inner product, and it is a complete metric space. So here, let's describe how to. So here are just some introduction to the notations in quantum computing. And typically, for example, we consider H. It is like 4 dimension, for example. So this means each vectors in this Hilbert space can be represented by a complex vector of 4 dimensions. So typically in the direct notations, we will denote a vector by this kit notation, kit phi, and you can represent it as a vector. And here I will write it in the basis, in the standard basis of this Hilbert space. So let's assume this space is spanned by some basis vectors. It's spanned by 0, 1, 2, 3. So these 0, 1, kit 0, kit 1, kit 2, kit 3, they are a set of orthonormal bases of the Hilbert space H. And then any vectors or any states in this Hilbert space can be represented by a linear combination of these basis states. Alpha 0 plus alpha 1 plus alpha 2 plus alpha 3. And all of these coefficients are complex. And we can define the inner product to define the inner. So this vector, it corresponds to a column vector. You can also write it as a matrix if you are more familiar with the matrix arithmetic. So you can represent this vector as in the column vector form. So it is alpha 0, alpha 1, alpha 2, alpha 3. Great. Now we will define another notation, that is, you reverse the direction of this kit operation, kit notation. You have this bra notation. So bra notation represents a vector in the dual space of this H. So it actually corresponds to those row vectors. So this, for example, we write it this way. We can also write it 1, 2, plus 3. Okay, and it corresponds to this row vector. Here star just represents some complex conjugate. Okay. So the inner product of these two, actually we should say the inner product of kit psi and kit phi is then you just multiply these two vectors by the standard matrix multiplication. So we often denote the inner product by this way. We just, it's in the direct notation, every inner product or other matrix arithmetic can be using these simple multiplications. So it is denoted in this way, and it is just the sum over or alpha j times beta j star. And you can also obtain this inner product by multiplying this row vector with these column vectors. Okay. And we need two additional conditions for a state or a quantum state. So we add two additional conditions, A11. So each quantum state has its norm. So the norm is defined by the square root of the inner product with itself to be 1. So it is all normalized. Also, we need to identify some quantum states of different mathematical form, but they are equivalent in physics. So we are, for any theta, then we consider these states to correspond to the same quantum state. So that means if you multiply by an arbitrary phase, this is called a global phase, before any kit per psi, then it is the same quantum state. Okay, this is the first axiom. Now we know what is the state of a quantum system. And we give an example of that. Okay, so let's move on to the second axiom. Second axiom. Okay, let me mention one point. If H, if it is just isomorphic to a two-dimensional Hilbert space, then this is often called, so in this case, this quantum system is often called a qubit. So a qubit has two-dimensional, it lives in the two-dimensional Hilbert space. And the second axiom is saying the space of two quantum systems, A and B, that means the composite system of A and B is the tensor product of their corresponding Hilbert space. So if we denote the Hilbert space for this composite system of A and B, then it is represented by this tensor product, HA tensors product with HB. So let's try to write this Hilbert space AB. If you have, so let's recall what is the tensor product. So if you have a vector, say psi, that is alpha 0, 0 plus alpha 1, 1, and you have another vector beta 0 plus beta 1, 1. Then their tensor product, you are just multiplying. So this is often right in this way. So you just multiply the 0, 0, tensor 0 plus 1, 0, 1, 0. Where these form a new basis for this Hilbert space HAB. Okay, so HAB is just the span of or psi phi, where the psi is in HA and B. Sorry, phi is in HB. So as you can see here, we have this span. That means not every state in the composite system can be represented by a tensor product. So those states are called entangled states. And here is an example of that. So a typical entangled state, here we have the notion of quantum entanglement. Oh, okay, I forgot one thing. So this is often considered as the superposition of 0, 1, and 2, and 3. But since we are talking about the mathematics, yeah, you can just regard it as a vector. Yeah, that's true.
What does span mean?
A span is, so you just take the linear combination of these basis vector. So that means...
It's not basis vector.
I'm sorry?
I mean, phi and... so in the parentheses, is it a basis vector?
Actually, you don't need to take it as a basis vector, but basis vector also suffices. So, so suppose you have, okay, let me try to write it.
So it doesn't have to be basis vector, right?
Yeah, it doesn't have to. You take the span of all vectors. But you can also take this basis vector, and they will also, their span is also this. Yeah. Okay, great. So what is quantum entanglement? So here is an example of so-called EPR state. One of EPR state is like this. So here is 0, 0. Let me first write it in this way. 0 plus 1 plus 1. So here I use the subscript AB to indicate which system this vector belongs to. So as you can see, this vector, it should be in the composite system because it is a linear combination of these tensor product. But not unfortunately, but this quantum state cannot be represented as a product. So it does not equal to some psi tensor product with some phi for psi and phi in A and B. So in this case, we say there is some entanglement between the system A and B. Okay, and there is just some notation convention. If we have this tensor, we often will write it, use a more simplified notation like in this way, or just write 0, 0. And also, I would like to mention, if we note that the dimension of the composite system HAB, its dimension is dimension of HA times dimension of HB. So that means if you have n qubits, so each qubit, if you have n qubits and each qubit has a Hilbert space H2, you need to tensor it n times. And if you consider the dimension of the n qubit, it will be 2 to the n. So that's why if you don't have much background in quantum computing, that's why some news or other literature often says a quantum state can encode some exponential information in its. But in quantum computing, even if it encodes that much, it singly encodes that much classical information, you cannot extract that much from the quantum state. So that's a restriction on quantum computing. Okay, great. So now we finished the first two axioms. So we know what is the state in what is the quantum state and what is the space corresponding to the composite system of the composite of quantum systems. Now we have the state. So what is the operation? So the third axiom is about operation, and here we only consider one type of operation called unitary. So it describes the evolution of the closed quantum system. So this is evolution of a closed quantum system. It's a unitary operator. It's a unitary. That's just to say it is unitary. U. So what is a unitary operator? If you describe it as a matrix, then it's a matrix satisfying this condition. U dagger times U equals to U times U dagger equals to identity, where U dagger denotes the you first take the transpose, or then you take the complex conjugate. So these matrices are defined to be unitary matrix. And what does it mean by an evolution of a quantum system is unitary? That means all valid transition between quantum states are applying a unitary to some, I should write it this way. So you can apply a unitary to this psi to make it to transform it into U psi. So that's what operations are available for you in quantum computing for closed quantum systems. So here I will give you some examples. What are typical unitary? So if this psi is the state of a qubit, then the U we consider is x on, it is the operator x on 1 qubit. So what are typical 1 qubit unitaries? We have these Pauli operators. X is 0, 1, 1, 0. And you can easily verify it as a unitary. And we have 3 Pauli operators. This is 0 minus I 0. And Z is 1 minus 1, 0. Okay. And we also have other unitary. This is called a Hadamard gate, which is square root of 1, 1, 1 minus 1. Yeah, let's do some calculation. So this state is this unitary. If you apply this H to some basis, so here 0 is one of the basis quantum states. If you apply it to 0, then it will become the square root of 0 plus 1. And we often denote this state by the plus. It is the plus state. So that means if you apply this Hadamard gate, these are called 1 qubit gate, 1 qubit quantum gate. If you apply this H gate to initial quantum state K0, then it will be transformed into the plus state. And there are also other types of 1 qubit unitaries. I will mention one more here. T is defined as 1 to the e to the I pi over 4. Okay. So these are typical. There are other, but I will just mention this 5. Okay, let's mention some other examples of 2 qubit unitaries. And probably the most typical one is C0. So what is the definition of C0? I will use some new notation. You can write it in this way. And C0 is somewhat related to our topics. So here, this notation, you can think of it just as you are taking the matrix multiplication of these 2 vectors. So these 2 vectors represent the column vector and the row vector, and you take the product of this matrix, and it will give you 1, 0, 0, 0. So here, tensor is still the normal tensor product, and this is similar. So if you write the matrix form of C0 gate, it will be equivalent to 1, 1, 1, 1. 0, 0, 0, 0. So what's the intuitive meaning of the CNOT state? So it is conditioned on the first qubit. So here it is a 2-qubit gate. So this part conditioned on the quantum state of the first qubit. If this first qubit is in state 0, then you do nothing. Otherwise, if it is not otherwise actually, if it is in state gate 1, you apply an X gate, where X gate will flip the value of this quantum state. So remember, if you apply X to 0, then it will become 1. If you apply 1, it will become 0. So you can verify this by just checking the matrix form of X. Okay. And of course, a state, the first qubit, the controlling qubit, can be in a superposition state. So if we apply C0 to some state like, let's say we start with some state 0. This is just plus 0. If we apply C0 to this 2-qubit state, then it will become, so here it is square root of 0 plus 1, 0. Okay, then if the first state is in state 0, then you do nothing. If the first state, the state of the first qubit is 1, then you flip this the second qubit, so it will become one of the EPR state. It will become this state. So that's the C0. And of course, you can define other 2-qubit gates. And now let's wrap up this part. So typically, we will consider 1-qubit and 2-qubit quantum gates to be the elementary operation in quantum computing. So that means if you want to construct the quantum algorithms, then you can write it as a quantum circuit. And this quantum circuit contains 1 and 2-qubit gates. This is an example of a quantum circuit. And often since quantum algorithms often provides computational advantage, that means we measure the number of gates in this quantum circuit as the complexity of these quantum algorithms. Okay. And actually there you can find a universal gate set that approximates any 1 and 2 elementary unitary gate. Yeah, just I briefly mentioned the C0 is often denoted by this notation in quantum circuit language. But today we are mostly talking about the programming, so we have other ways to denote this gate. Okay. Now the final axioms is about the measurement. But since we don't have too much time, I will not dive into this. The fourth axiom. So it's about the measurement. So previously we talked about what is the quantum state and how the quantum state evolve in the closed quantum system. But that does not give you any information. If you are human, you want to learn some information from the result of a quantum computation. You need to obtain some classical information. But all we have talked about happens in the quantum world, and you don't have a way to obtain some classical information from that quantum state. So there's another operation called measurements, which connects the classical and the quantum world. If you make a measurement, you are using some device and use it to measure a quantum system, then this device will be entangled with this quantum system. then you can learn some information from that device. But I will not talk about the measurement today. What we all need for our topic will be the unitary, and that's enough. Okay. Okay, great. So that's a background for quantum computing. Is there any questions? No? Okay, great. Now we can talk about the programming part. Okay, I will just give you some intuition about the quantum recursion, but today we might not have enough time to talk about the formal definition of quantum recursion. So what is the intuition for quantum recursion? The intuition is quantum recursion is a combination of two programming features. So the first feature is called quantum control flows. So remember, in classical control flows, we might have statement like this: if then else statement. So if some b equal to 0, then we do something, c0, c1. Otherwise, we do some other things. And this is your program. You have very complicated control flows inside this program, like this if then else statement, or iterations, or loop, or recursions. And your data goes into the input, and after this program, you have some output. And now for a quantum program, the input and output and all the states during the program execution are quantum states. And what about the control flow? So a quantum version of this if-then-else statement is called quantum if statement. So we will use QIF to denote such kind of statement. So QIF, it will condition on a qubit instead of a Boolean expression. So here Q is a qubit. It can be in a superposition state. And Q, when it is in state 0, kit 0, then we execute some program C1, C0. When it is in state kit 1, we execute some program C1. So here we just reverse the if and reverse the QIF to put the statement inside, to put it into a statement. Yeah, okay. So what does this mean? If you think of it this way, the classical if then else, the control flow goes to here, and you check whether b is equal to 0, then you only go one way into these two branches. So here is the first branch, here is the second branch. Classically, you just check this condition, and you only go one into the two branch. But in quantum, the control flows arrive at this Q, but Q, it can have a state in superposition. So it can be in some state alpha 0 plus beta 1. And it also have two branches, C0 and C1, but we go into these two branches in superposition. That means you have some amplitude alpha to go into the, so alpha and beta are called complex amplitude. So you have some amplitude alpha to go into the first branch to execute the first statement and have some amplitude to execute the second statement. Right. So what is, if this C0, it describes some unitary. The unitary is what operations we can do. If C0 describes some unitary, so C0 is a program. And it can describe some unitary, U0. And C1, it can be described as unitary U1. Then after the whole QIF statement, you obtain some state. Like, so if you start with some alpha 0, psi 0, plus psi beta 1, psi 1 state, then after executing this QIF statement, we will have U0. You apply the U0 on psi 0 plus beta 1, U1, psi 1. So that means you are conditioned on the first qubit to decide you want to go with which was the branch. And it can be in superposition. Okay, great. So that's one feature of called quantum control flows. And we also need recursion.
Sorry, quick question.
Sure.
So this is you define the quantum control flow using 1 qubit, but have people thought about using 2 qubits or micro qubits?
Yeah, you can construct it using this one. So, so you just go into 2 branch, then you can have another control to go into 2 branch. So that means you have 2 qubits to control the quantum, to define the quantum control flow. But here we just, since we are constructing the primitive, we just choose the simplest one, right? Okay, so that's one feature, and if we combine it with the second feature, then we have the quantum recursion. And we will see why this quantum recursion is complicated. I should not erase this.
Yeah, but again, sorry. So what you said makes sense. But then the thing you just erased, the basic says that if this Q equals to 0, you're gonna apply an unitary matrix.
Yeah.
But then the construction you just mentioned is that if this Q equals to 0, you're gonna apply another if. So, but then the other if, is that another unitary matrix or not? That's the thing that I don't know yet.
You're asking the 2 qubit case?
Yeah, yeah.
Okay. So if you, so the original version of our definition of QIF statement is you can condition on any qubit, number of qubits. But from an implementation perspective, we want to construct the program in the simplest form. And we can write a more complicated form in using those primitives in the simple form. But if you have 2 qubits, for example, then these 2 qubits can have so it can have 0, 0 to do some C0, 0, 1, 0 to some 1, 0. So here the square is called the Dijkstra dotted command. So it just separates different cases. And if you have 1, 0, you have to 0, 1, or 1, 1, you do C 1, 1. And of course, Q1, Q2, it can have the quantum state to be a superposition of these 0, 0 plus alpha 0, 1 plus alpha 1 plus alpha 1. It can be a superposition. And you can write it in this way. This is equivalent to Q if you first condition in Q1, then you write a nested Q if Q2 and zero to C0, 0 plus write it this way. Q Yeah, you can already see what's happening here.
Yeah. So that was yeah. Thank you. So I think that explains the way to decompose it into your QEF using one bit. But that question was slightly different because I think in the previous example you mentioned that what's going to happen over there is that you're going to have a unitary matrix representing C0, another unitary representing C1.
Yeah.
What was not so clear to me was that allowing this if, QIF, would that be also, I mean, I think the answer is yes, because eventually you're going to translate this into some unitary matrix. So this QEF thing is your syntax, but your semantics can be implemented using the unitary matrix.
Yeah, you're right. I still haven't talked about the syntax and semantics, those formal definitions here. I just try to give some intuition about. But yes, if C0 and C1 are implemented by unitary, then this whole cube statement is also implemented by another unitary.
Thank you.
So here, all we talk about are just about unitary because this is just one, like the first step in this direction. So let's start with the simple one, and we don't consider any measurements. Yeah. Okay. Great. So this is the first features, and we combine it with the second feature. This is what we have seen before, the recursive procedure call. Then this gives you the quantum recursion. And the caveat here, is these two features, they can be combined in an interleaving way. So that could be very complicated. For example, you could, let me see. So let's take the example of classical divide and conquer. In divide and conquer, you will divide a problem of size n into two smaller problems, n over 2, n over 2. Then, for example, you first decompose it into these two problems, then you conquer each of them, then combine the result, you obtain the result for the original problem. But if you have quantum control flows, you can do quantum divide and conquer in this way. So you have a problem of size n, then you decompose it into n minus 1 and minus 1. You are conditioned on the first qubit, and so you are combined them using the quantum control flows. So here actually they are in kit, and here we have the first qubit, 1. You can combine it in this way. So this is also known as decrease and conquer, since each time you only decrease 1 qubit. So you can do this way, and each n minus 1 you will use another recursion to you just recursively apply this procedure. So this is more complicated than the classical case, and I will draw a diagram this will help you to think about this quantum recursion. So each time you can create two quantum branches, and they can be in superposition. And at some point, you might go back to recursively call the procedure itself. So you have, and these two features can be interleaving. So yeah, that's too complicated. So that's why we need to study it from the programming language perspective, because it is a formal way, and it can the programming language itself is essentially defined by some structural induction. So that is a better way to understand how you interleave different primitives. Okay, great. So that's the intuition, and I think today we don't have enough time to go to the very definition of quantum recursive program. But we will start with some background in programming languages. So let's get into some formal details. Okay, so now the second background. But when I talk about the background, I will also already introduce some quantum programming languages, and we will go through we will go along this way, and at the end we will arrive the definition of quantum recursive program. But that might be the content of next lecture. So let's just start this journey. So let's define a PL for a programming language for quantum recursive programming. And I will talk about first the syntax, and I will also talk about the semantics. So syntax basically tells you how to write a program, and the semantics tells you how to interpret that program. So both parts are important. Originally the semantics is not made formal during the early age of programming language. So we have a lot of definition of different programs, but when two programmers look at the same program, they may have different interpretation of that. And okay, so we will develop a series of programming language. We're starting from the simplest one, which is a language for describing quantum circuit. Then we go to QC+, and we will embed this language into this more expressive language, adding some additional feature, and this additional feature is classical variables. And we will further extend it into RQC++, that is add the recursion without parameters. And finally, we will obtain this language called RQC++. We will add recursion with parameters. So we will do this in this line, and this is the work from the work done jointly with Ming-Shen, but he's leaving.
What does recursion with parameters mean?
Sorry? Oh, okay. So recursion with parameter, so remember we can define some procedure with some parameter, like n. And we can define it using itself with a different parameter, like this.
Okay, got it.
So that's the parameter. But in this language, we don't have these parameters. Yeah. This is in the first of our paper in this direction. And I will, in the remaining of this lecture, just 15 minutes, and the next lecture I will talk about how we define the syntax and semantics for the quantum recursive programs. And in the following 3 lectures, I will talk about how to implement such kind of program, including its compilation and some related stuff. Okay, great. So today, let's just start with the simplest one, the quantum circuit. So first, what is the syntax? Syntax. Here we write definition. So remember, syntax tells you how to define a language. So here we will use the, sorry, I need to first mention some notions. So previously we are talking about the quantum circuit, but when we consider programming, we need to deal with variables. So here first we need to mention what is a quantum variable. Just like classical, you have a lot of variables, and you can make some computation arithmetics on these variables. So what is the quantum variables? So quantum variables, we will denote it by the set of all quantum variables by this notation Q bar, and And we also often use Q or Q1 or Q2 or something to represent the quantum variables. So quantum variables, it has some state, and the state is a quantum state. So a Q, we will associate with Q with some type. And this type is a Hilbert space of this of some quantum system. So Q, you can think of it as a quantum system, if you like. And this HQ can be, for example, H2, then this is called a qubit. This Q is called a qubit, or whatever. H8, it could be some qubit of dimension whatever. Okay, so this is a simple quantum variable, but we can also have more complex quantum variable. So we can have an array, a quantum array. So a quantum array is similar to a classical array, but you know the quantum, the superposition will create something different. So if Q is a quantum array variable, then its quantum state, let's consider the same thing case. For example, it is one-dimensional qubit array. So what is one-dimensional qubit array? Let me just show you an example. So you have a lot of qubits put on the array. So here there are 8 qubits. So, so this first one we will call it Q1, Q2, to Q8. So what is the type or the Hilbert system corresponding to this whole array? It should be the composite system of this qubit, right? So the type of this array variable would be tensor product of some J. J is the index of some classical type. Let's say T. T is stands for the classical type for that index, and here T is some integer. So integers starting from 1 to 8. So T is J is lies in some type integer, and we tensor product of all these Hilbert space, that is T. Sorry, should be H. So since we are assuming each of the qubits has type, each of these quantum variables is a qubit, so they all have a type H2.
One question, is that the different notation Q sub 1 and Q1 on low are different?
Sorry, which one?
Yeah, their one and the low ones are different.
Yeah, they are different. So each of these Q is a quantum variable. Yeah, and quantum variable can have, we can have different quantum variables. So this one is called simple one, and this one is called array, quantum array. So here Q, this whole array, we can just call it Q.
Is it like the vector Q? That one?
Sorry?
Is it the whole, that Q is, the Q you just mentioned?
The whole Q.
The whole Q, I see.
Yeah, and this Q is in quantum variable. Yeah, so it's just a symbol. So actually call, so here we first start with some alphabet. And alphabet tells you what symbol you can use in this, in describing this program. Yeah, and of course you don't want to use all kind of symbols, because that would allow you to have some natural language, and that will contain a lot of ambiguity. So we are making some specifications. Yeah, so this whole array is called a Q, and each of these Q, each part of the Q, we can use this Q1, Q2, Q something to denote the component of this array. Yeah. Questions? No questions? Let me check the time. Okay, 10 minutes, enough. Okay, so this is a quantum array, and a quantum array will induce the so-called subscripted variables. subscripted quantum variables. So what is subscripted quantum variables? We can write something like this in the program. We can write x plus 7, y minus 2. So this is a two-dimensional, Q is a two-dimensional qubit array. So I will not explicitly write this type, but Q is a two-dimensional quantum array. And here, x and y, they are classical variables. So this one is, again, it is also a quantum variable, but it is induced or subscripted from the quantum array Q. And what it means is you are considering the x plus 7s, and the first index is x plus 7 and the second index y minus 2. But we leave some degree of freedom here. So x is some classical variable, and x can take different values, right? If x is equal to 1 and y is equal to 3, then this refers to Q 8, 1. Let's just take the one-dimensional case. It's simpler. So if x is equal to 1, then it's Q8. So it refers to this one. But x can take different values. The x can also be minus 3, then it refers to Q4. Yeah. And you can use this x. For example, you can write some for loop. For x is equal to 1 to 8, then I do something u on qx, right? You can write something like this. So you are doing the iteration, and each time you apply u to on some qx, and x is enumerated from 1 to 8. This kind, just like the classical programming languages. But the greatest difference is that the type or the state of the quantum array should be composed in the quantum way. So there could be some entanglements between different qubits. They can be in the entangled state instead of product state. And that's a major difference between quantum and classical variables. And we also have, so this is the first set of alphabet. We also have another alphabet. Let's denote it.
Question there.
Yeah.
So you raised an interesting point. You're subscripting an array of qubits,
Yeah.
which may not be in a product state. They
Yeah,
can
of
be
course.
entangled. So what does it mean to subscript an entangled
Okay,
state?
good question. So you are asking what is the state of when you subscript this Q2?
Yeah.
And actually, we won't describe this state. We have to describe the whole state. Because, of course, you can, if you know some quantum, of course you can consider the partial density operator corresponding to this subsystem. But that means you implicitly measures out all the other qubits. But in our programming language, we will always describe the state of the whole system. So it is complete description. And these subscriptive variables are used, and you describe how you perform the quantum computation. So we actually won't consider what is the partial state of some subscripted variables. Okay, and we have another alphabet called U, calligraphy U, which contains all elementary. So it is a set of elementary unitary operation, unitary gates. Let's just say elementary unitary gates. So one choices of U could be you just choose it to be like all the 1 and 2 qubit gates we previously mentioned. Whatever you can choose it. Depending on your interest. T. Okay. Now we have the alphabet, we can define the syntax. Probably today we only have the time for the syntax. Yeah. I will just talk about the syntax, then we can conclude. So the simplest quantum circuit language had the following syntax. So here I will use a standard BNF form, Backus-Nauer form. To describe the syntax. So it is bistructural. So it is like the recursive definition. So C is a statement or circuit. It can be U applied to some Q. Okay, let's just think about U to be 1 and 2 qubit unitary. So it can be U applied to some single quantum variable, or it can be two sequential compositions and QF. Let me finish the writing and explain. 0 to C0, 1 to C1. Okay, so what does this mean? That means C can have the following forms. Either it can be a unitary apply some quantum variables, or C can be this is called sequential composition, which is also in classical computing, you can compose two quantum circuits. So a circuit can be a unitary apply some quantum variables. It can be a composition of two different other C, where each of these C also have this form. So it is a recursive way to define this. And here, C can also be a quantum if statement, where each of these C0 and C1 also satisfy this form. So you can use this to define recursively complicated quantum circuit. So I will give you an example. So for example, C can be, just say, you first apply the H on Q1, then you do C0 on Q1, Q2. So here we just use these two statements. You can also write it another C. It can be just a QF, some Q1, and 1, 0 to perform I identity on Q2, and 1 to X Q2. Okay, so the second program or circuit or whatever statement means you are conditioned on Q1, on the first qubit Q1. If it is Q0, then you just do nothing on second qubit. If it is 1, then you perform an X gate on Q2. So this is equivalent to, equivalent to C0. Q1, Q2. So this is exactly the very definition of C0, but we can write it in this way. Of course, QF can describe more complicated things, but this is just an example to illustrate what the QF is doing. So this is the syntax for the simplest quantum circuit, the first language, and I think the time is, yeah. So in the next lecture, I will continue to develop that series of programming languages, and we will arrive at a language for quantum recursive program. And I will also mention the semantics, the formal semantics of this program. Yeah, that's it. That's the end of today's lecture. Thank you, everyone, for attending.